Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we are looking at osmotic pressure. So let's start with the first problem. We have three problems that work through with osmotic pressure, each dealing with osmotic pressure. So we're asked to calculate the molar concentration of fructose that is isotonic with seawater, given that the average osmotic pressure of seawater is 30 atmospheres at 25 degrees Celsius. This is very, very straightforward. You only have so many equations with osmotic pressure. There's actually only one equation with osmotic pressure, but there is a variant on it. So we're going to deal with just the one. And it's this one question, this one equation is osmotic pressure, which is symbol pi, is equal to molarity times a gas constant times temperature. Okay? So what we need to calculate here is actually the molar concentration, or molarity. So we're going to manipulate our formula. Molarity is equal to pi, osmotic pressure, over our gas constant times temperature, which we're given our osmotic pressure, which is 30 atmospheres. Our gas constant is 0.0821 liter atmospheres per Kelvin mole. And we have to put our temperature in Kelvin, so 25 plus 273 is 298, so 298 Kelvin. And so when you do that calculation out, you end up with 1.23 molar. And that's all there is to it for that one. Relatively simple. Our next problem asks 53.0 grams of a substance is dissolved in enough water to make 1 liter in volume. We're going to have to remember this. 1 liter. That's going to prove important here in a moment. The osmotic pressure is found to be 20 millimeters of mercury at 25 degrees Celsius. Calculate the substance's molar mass. So we know the calculation for osmotic pressure is pi is equal to mRT, and we know that molarity is equal to pi over RT. So now we just need to find out, can we do it with just the information what we're given? Well, first off, we're going to want to change our millimeters of mercury into atmospheres and our degrees Celsius into Kelvin, because that's the gas constant that we have. We could always convert the gas constant to be in terms of millimeters of mercury and in terms of degrees Celsius. I just find it easier to go ahead and change everything else instead of having to memorize a new gas constant. So let's just go ahead and do that. So our pi is going to equal 20 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury, which is going to equal 0.0263 atmospheres. And then for our temperature, we have 25 degrees Celsius. Add 273 to it, you have 298. Don't think we need to display that. So overall, we're going to plug in our information. So 0.0263 atmospheres divided by 0.0821 liter atmospheres per Kelvin mole times 298 Kelvin gives us a molarity of 1.07 times 10 to the minus 3 molar. Recall that we're dealing with 1 liter. And we can rewrite molar as moles per liter. And if we only have 1 liter, then our liters cancel out and we're left with 1.07 times 10 to the minus 3 moles. Now we're asked to find what the substance molar mass is, and we know what the mass is, and we know what the moles are now. So if we look at the unit definition of molar mass, it's grams per mole. So all we have to do is take 53.0 grams and divide it by 1.07 times 10 to the minus 3 moles. And what we're left with is our molar mass, which is 4.95 times 10 to the 4th grams per mole. That is a massive, massive molecule. Yeah, that's probably something in the field of biochemistry, like a protein or something of that nature, to have something molar mass that large. Our last problem states the osmotic pressure of a 0.020 molar potassium iodide solution at 25 degrees Celsius is 1.22 atmospheres. We're asked to calculate the Van Hoff factor of the solute at this concentration. Now, recall earlier in the video, I stated that there is a variant on our osmotic pressure equation, and that variant includes the Van Hoff factor. Oftentimes we don't have to include it, but sometimes we do. And all it is that instead of it just pi is equal to MRT, it's pi is equal to IMRT. So we simply solve for I, which is our Van Hoff factor. I is equal to pi over MRT. Now, T is going to be 25 degrees Celsius, which in Kelvin is 298 K. We're given our molarity. We're given our osmotic pressure. So overall, we have everything. We only need to convert temperature. So plugging in all of our values, we have 1.22 atmospheres divided by 0.020 molar times 0.0821 liter atmospheres per Kelvin mole times 298 K. Looking at this in terms of units, molar is moles per liter, so as we cancel that out, we cancel our moles and liters. K cancels out, and atmospheres cancel out. So you come to find that the Van Hoff factor is a unitless figure. And when you do the calculation out, your Van Hoff factor is 2.49. And that is the sum of some osmotic pressure problems.